Hey guys, this is Calc 1, linear approximations and differentials. So linear approximations are used to approximate values that are hard to do without a calculator. So examples are like the square root of 2.9, cosine of 8.3 degrees, and so on, things like that. Obviously, the calculator is very simple, but without a calculator, they're rather difficult, but that's when linear approximation comes in. So there's a formula for it, as pretty much everything in math, which is L of x equals f of a plus f prime of a times x minus a. Now, believe it or not, this is the same exact thing as finding the tangent line to a curve. So really, in my humble opinion, I think finding a tangent line to a curve to approximate these is much easier than doing this formula. Because for one thing, yeah, okay, you can derive the formula and all that, but chances are you're going to just memorize it, right? And it's just something that you have to memorize, and it's not really necessary. So I don't believe in memorizing things that aren't necessary. However, I can prove to you that it works both ways. So, for example, suppose I want to approximate the square root of, I don't know, 15.2. Okay. So first off, you got to have a function that's going to represent this, right? The square root of 15.2. Well, it's a radical, right? So what's the function we could use to represent that? It's closest to it. Well, a radical function, which is f of x equals the square root of x or x to the 1/2 power. So since we have f of x is equal to x to the 1/2 power, well, we have to find the first derivative. So f prime of x is going to be 1/2 and then negative x to the negative 1/2 power, which we can just rewrite as 1/2 x to 1/2 power. So with using the formula L of x, well, first we have to know what value of a we're going to use. Well, a value that's close to 15.2, that's easy to take the square root of. Well, that's easy. 16, because the square root of 16 is just 4. So that works out smoothly. So it's going to be f of 16 plus f prime of 16 times x minus 16. Well, f of 16, plug that in, it's 4. F prime is 16, you're going to get 4 here, times 2, it's 8. So 1/8 x minus 16. So then it becomes 4 plus x over 8, or 1/8 x, and then 1/8 times negative 16 is negative 2. So then that means L of x is x over 8, and then 4 minus 2 is 2, plus 2. So now, if I want to figure out the linear approximation of the square root of 15.2, well, I plug in 15.2 in for x. So equals 15.2 over 8 plus 2, which, if you did the calculation by hand or calculator or whatever, 15.2 divided by 8, and then add 2, that's just going to give you 3.9. Now, let's see how close this actually is. Well, the square root of 15.2, when I plug it into a calculator, gives me 3.8987. And as you can see, it's very close to 3.9. So it's a good approximation. Well, now suppose, as I mentioned before, we were to do it such that we're trying to find a tangent line to a curve. Well, we pretty much have a lot of the information. Because number one, if, again, f of x, we know, is equal to x to the 1/2, and we can use 16. So f of 16 is just 4. Or we can just say the point, 16, 4. And we know that the first derivative is just 1/2 x to the 1/2 power. So first off, I plug in 16 into here. Square root of 16, or 16 to 1/2 power, is just 4 times 2 is 8, so 1/8. So m, our slope, is 1/8. And then y, we can use, well, slope-intercept form, or point slope form, whatever way you want. So the slope is 1/8, so y equals 1/8 x, or x over 8, plus b. So then, just using some algebra, if you plug in the values here, well, what does y equal? Y equals 4, and since y is 4, and then x is 16, 16 divided by 8 is 2, then plus b. B is just going to be 2. So then we just use y equals x over 8 plus 2. And you see, look what we have. Y equals x over 8 plus 2. L of x equals x over 8 plus 2. So if you plug in 15.2, you get the same thing here, 3.9. So again, you can use linear approximation formula or tangent line, or find a tangent line to a curve at that point. I personally think tangent line to a curve is much easier. So another one is, suppose I want to figure out sine of 2.5 degrees. Well, first off, what function should we use? Well, if we're trying to find sine of 2.5 degrees, well, we use a sine function. We'll make it a simple regular sine function. F of x equals sine of x. And we want to pick a value that's close to 2.5 that also gives us a nice number. Well, going back to trigonometry, well, 0 is close to 2.5. Excuse me, 0 degrees is close to 2.5 degrees. And sine of 0 is just 0. So that means, okay, f of 0 equals sine of 0 equals 0. So f of 0 equals 0, or the point 0, 0. So if we want to find a tangent line to the curve or linear approximation, well, first off, the derivative of this function, derivative of sine, is cosine. And then now I have to plug in 0 for x in order to get my slope. So f prime of 0 equals cosine of 0. Cosine of 0 is 1, which is just my slope m. So y equals x plus b, and I want to find the point 0, 0. Well, if you plug in 0 for x and y, you get b equals 0. So that's very easy. So y equals x. Okay, well, now I want to figure out what sine 2.5 degrees is. Well, I would have to plug in 2.5 into here. But that would be saying y, that would mean that sine of 2.5 is 2.5. So it doesn't really make sense, because how could sine of 2.5 degrees be 2.5? So really what you have to do is you have to convert those degrees to radians. So we do this. And, to get a rough idea what it is, you plug into a calculator. Okay, 2.5 times pi divided by 180. It comes out to 0.04. If I run it to 4 decimal places, it's going to be 0.0436. So then if I plug this in for x, that's what sine of 2.5 degrees is going to be. Well, let's just see how accurate that is. So if I were to plug sine of 2.5 degrees into a calculator, make sure that I'm in degree mode, that winds up giving me, well, .0436. So it's actually the same thing. So actually that one worked out very smoothly. But now let's get into something else. Suppose I want us to figure out a change in a function's value. So suppose I had the function f of x equals x to the ninth minus 2x plus 1. And I want to figure out the change in the function's value from when x equals 1 to x equals 1.05. So really to figure out the change, if you just look at the basic idea of, okay, well, we know y is equal to f of x, all right? So if I take the derivative with respect to x to both sides, it's going to give me dy dx equals f prime of x. And since I want to find the change in the function's value from when x is 1 to when x equals 1.05, then that means that it's finding the change in y. So multiply dx over here. You get dy is equal to f prime of x dx. So first things first, dx is a change in x, dy is a change in y. Well, it's the same thing as saying delta y over delta x. So first off, dx here, or delta x, same thing, is the change in x. Well, it's starting from 1 going to 1.05, so how much did it change by? 1.05 minus 1, 0.05. So that would be our dx. Whoops, let me redo that. So first off, well, f prime of x. Well, again, we're trying to find the change in the function from when x equals 1 to x equals 1.05. Well, we already know that the change in x is 0.05. And since it's changing from this value from 1 to 1.05, that means we want to plug in this into our derivative. Well, first off, what is the derivative? We know f of x is x to the ninth minus 2x plus 1. So f prime of x is just gives me 9x to the eighth minus 2. So then now I have to plug in 1. So f prime of 1, well, this is actually easy. You get 9 minus 2, which is 7. So therefore, to find the change in y, it's just going to be f prime of 1 times dx, which is 0.05. F prime of 1 is 7. 7 times 0.05, that's just going to give me 0.35. So that is the change in the function from when x is equal to 1 to x equals 1.05. So it's literally just 0.35. And that'll basically do it for this. Keep in mind, there's also questions that involve, geometry, things like that, like, finding the change of a function's surface area given, a parameter changes, like, oh, what's the change in the volume of a radius from when the radius is 2 to a radius equals 2.85, things like that. And I hope this helps, and see you guys next time. Bye-bye.